Cqrs. And here's what we have. Software systems serve a variety of purpose from their first day, and the requirements on them grow over time. Changing requirements may pertain to a change in business logic, scaling needs, or some other aspects of the system. Satisfy these contradictory or overlapping requirements. Engineer must make a variety of trade-offs in the design of the system. Problem in making trade-offs is that many of them are not required at the beginning, and by the time their need arises, system design has evolved in such a way that the trade-off cannot be made at all. In my opinion, the most pernicious incidents of the design getting locked happens at the data layer. A typical application data model is designed by marrying domain knowledge with performance considerations. The domain knowledge dictates what the entities are and how they relate to each other logically. Performance considerations dictates how they were implemented physically. RDBMS versus NoSQL, primary keys, indexes. These two set of choices together enable an application to serve its use case efficiently. In large application with a lot of data and complex entity models, some implementation details become core over time. This is sometimes explicitly done by engineers, but often it happens in an unstated or even inadvertent manner. In these situations, new requirements can be so far at odds with the existing implementation that, that they cannot be accommodated at all. This general class of problems is large with different solutions for different cases. In this article, I want to focus on the problem that arise when the way data is read from an application is very different from how data is written to a system. Difference can be in terms of query patterns, output format expectations, or scale at operations. Uh, I wrote about my encounter with this situation. The order management system I was working on at the time was optimized for working with entity IDs, but over time, complex read requirements emerged which the data model was unable to support. Problems were twofold. New query patterns were emerging, which were difficult to implement efficiently in the existing implementation. Far more worryingly, the readers of ordered data were beginning to expect a very different model of the data. Example, sellers on the e-commerce wanted their slices of a larger customer to be represented in a certain way. Customer-facing apps wanted the data to look very similar to how it looked in the cart. This is not uncommon occurrence, especially for systems that own the core entities of an organization. The data they encapsulate is so widely used that it is required to be available in many different formats. System itself needs yet representation to work with its data. How can we bridge this gap? CQRS. CQRS stands for Common Command Query Responsibility Segregation. Systems built with CQRS principle designed between data model used for command query. The command model is to perform write update operations efficiently, while the query model is used for supporting the variety of reads and patterns effectively. The data between the two models is kept in sync by propagating the changes in command model to the required domain events or other mechanism. If this sounds like two different let me point out a subtle difference. The physical implementation of these two data models can be indeed done or as two separate microservices. A single command model can even be used to support multiple query models. However, key constructor microservices represent two independent domains. In CQRS, both the command and the query models are part of the same logical domain, regardless of the running architecture. The query model cannot function without understanding the command model deeply. The coupling here is expected, however, unlike the decoupled behavior we hope to create in two separate microservices. CQRS does not dictate how the two models are kept in sync. This may be done synchronously by updating both the models at the same time. It may also be done asynchronously by transferring commands from the command model to the query model over a message broker life path. Latter choice is one made often because it creates a more scalable system though it comes with the obvious trade-off of eventual consistency between the read and the write operations. Isn't it just caching? A data model dedicated only for read sounds suspiciously like a cache. Read the query model can be implemented using a caching technique like Redis. However, the purpose of using CQRS is not just to separate the place where is written from the place the data is read. The fundamental intent is to create multiple representation of same data, each of which satisfy the need of the user. May have many query schemas, each of which may use a different physical implementation. Some may use the same database, some may use Redis. Is a useful architecture pattern. The first one I pointed out earlier, if the same data model later able to satisfy the right patterns of a system, then it makes sense to decouple the two schemas by applying CQRS. The resulting data model can then cater to these specific requirements. CQRS model effectively unlocks the data from a single representation into any number of representation, all of which are kept consistent with the core representation which handles all the data made to it. The second scenario in which CQRS is helpful in separating the read load from the write load. This may sound like cheating, which I have explicitly distinguished between caching and CQRS just a couple of paragraphs above. But hear me out. CQRS doesn't seek out caching as an objective. However, by separating the command and the query schemas, we can create the possibility of scaling work independent of the other. The query schema may live on a separate database and employ caching on its own. It may be implemented in a technology that better caters to the query patterns of a particular use case. In any of these cases, the command model is exempted from having to scale to the requirements of the query model. I would repeat that here that despite all this, these are not independent systems. The coupling between them is deep and not a problem. When should I not use CQRS? Using CQRS as a system introduces significant cognitive overhead and complexity. Instead of a single data model and technology choice, now I have to contend with at least two data models and potentially multiple technology choices. All of this is a overhead that cannot be ignored. Next problem is keeping the command and query data models in sync. If the choice is made to keep the updates asynchronous, the entire system is forced to deal with the fallout of eventual consistency. This can be extremely troublesome, especially if parts of the system are designed directly exposed to human users who expect their articles, actions to reflect in their data immediately. Even a system single requirement for consistency can impel the whole design. On the other hand, if we choose keep the model in a consistent state at all times, the cap theorem and two-phase commits come knocking around. If both the schemas are co-located on a single asset-compliant database, we may still be able to use transactions to keep them consistent. However, this takes away much of the scaling benefits of CQRS. If more than one query model is to be supported, the write operations will continue to get slower and slower since they need to update all query models before they can succeed. Both these problems make a proposition that should not be taken lightly. Judicial application, it can result in a highly scalable application, but supporting multiple data models is a tricky affair and should be considered only if there are no other means to satisfy the necessary query pattern.